Welcome to my presentation about a quantitative comparison of Monte-Carlo dropout uncertainty measures for multi-class segmentation. I'm Robin Camarasa, a PhD student at Erasmus Medical Center, and today, together, we are going to answer the following question. Which uncertainty map should I use? Let's motivate this research first. We are researchers of the field of Bayesian deep learning applied to medical imaging. This is a rising field, as we can see that most of the main challenges are creating tasks to assess uncertainties in medical imaging. And one of the main questions of scientists of this field is how to compute accurately uncertainties. So this is why it motivated our research, which is the first quantitative comparison of uncertainty map for multi-class segmentation in medical imaging. We applied this research to the segmentation of carotid arteries. So now I would like to guide you through the method thanks to this diagram. What we got with the Monte-Carlo technique is to several estimates. From those several estimates, we can have a segmentation and we can compute different uncertainty maps. Then what we did is evaluate each of those uncertainty maps in order to determine which one were better than others and if this difference was significant. Monte-Carlo estimates first. We used the technique developed by Gall and Gaussian in 2016, which is called Monte-Carlo dropout. Monte-Carlo dropout technique consists in sampling t sets of weights sigma 1 to sigma t and evaluate the segmentation for each of those weights and then ensembling the results. Two types of dropout were investigated in this research: the Bernoulli dropout and the Gaussian dropout. The Bernoulli dropout first, which I think is more familiar to you, as it's the one the more spread in the literature. It consists of dropping out the intensity of feature maps with a probability p, which is called the dropout rate, and rescaling the intensity of the other feature maps by a factor 1 over 1 less p. This is the impact of this Gaussian dropout on randomly sampled feature maps of the networks. As you can see, some are rescaled and some are shut down. Another possibility to compute dropout is to use Gaussian dropout, where instead of dropping out some features and rescaling others, all of the features are rescaled by a factor sampled from this Gaussian distribution. So this is the two dropout techniques that we used and investigated in our research. Now that we have the method to obtain several estimates at test time, let's discuss how we can get a segmentation map from those different results. Per class at a voxel level, we estimate the appearance of the output distribution by computing the mean of the dropout of the output computed with a different weight sampled with dropout. Now we will discuss the different uncertainty maps that we used in our methods. We used two different strategies to get uncertainty maps and 4 uncertainty maps, 2 per strategy. So let's see the first strategy, which is the distribution description strategy. For every distribution of the output at a voxel level and for every class, we can compute a description of uncertainty, as we can see in this diagram. Once we computed this description of uncertainty per distribution, we can average those descriptions, resulting in an averaging strategy. The associated uncertainty maps in the paper are the averaged variance and the averaged entropy. Another possibility is to take the two most probable classes per voxel and then compute their similarity. This strategy can be associated in our paper to the Bhattacharya coefficient uncertainty map and the Kullback-Leibler divergence uncertainty map. Then, now that we defined all of our uncertainty map, let's evaluate them. And to do so, I would like to point out that we modified a bit our diagram to introduce the misclassification, which is obtained from the segmentation and ground truth. We can get then the misclassification voxel-wise. And the question about the evaluation of an uncertainty map is, how good is my uncertainty map to predict misclassification? And this is based on the work of Mobini in 2019. So, to do so, and to answer this question, we're gonna define a new way of seeing true positive, false negative, false positive, and true negative for uncertainty. For a given value of threshold, once we threshold the uncertainty map at a value of th, every voxel can be defined as uncertain or certain. In the same way with the misclassification map, we have misclassified voxel and correctly classified voxel. Then, as we want to see uncertainty as a predictor of misclassification, we can define a true positive as a voxel that is uncertain and misclassified for a given value of threshold. From this, we derive the definition of precision and recall, and by integrating over all the different values of threshold, we can compute the area under the precision recall curve. So now that we evaluate our results, let's assess their significance. So the question about we want to answer in this part is uncertainty map A better than uncertainty map B? And to do so, we estimate the proportion of observation where actually the uncertainty map A is better than the uncertainty map B. Then we update this proportion via Bayes rules. For further details, I will let you read the paper. Now that we described in detail the methods, let's go to the data. As you can see, for every patient, we have 5 MR modalities that look quite different. From those 5 MR modalities, an expert could annotate the 3 classes: background, vessel wall, and lumen. The data are from the PlayCat risk study. It's a cohort of 3 centers, Amsterdam, Maastricht, and Utrecht, with 145 enrolled patients. We split it as follows. The networks were trained on 69 patients, validated on 24 patients. Both of the training set and the validation set are from Maastricht. And finally, it was tested on Maastricht, Utrecht, and Amsterdam data. The network used in our experiment is a 3D unit. However, there is a slight alteration of the 3D unit here, is that max pooling and upsampling are just 2D. This is due to the fact that the resolution on the Z-axis is way lower than the resolution on X and Y axis. We varied 3 parameters on these networks. First, the dropout type, either Bernoulli or Gaussian, as we discussed in the method section. Second, the dropout rate. And third, the training set size. This results in 144 experiments. Now that we defined the experiments, let's discuss the results. So the figures that you can see here is the distribution over experiments of the dice score averaged on the test sets. There are two key points to see in this figure. First, there is an important spread of the result, especially for vessel wall and lumen. This was intended in our design of experiment, as we didn't want to see how good was the uncertainty map in the best case scenario, but on every kind of scenario. Second, the different dice distribution, the dice distributions are really different for every class. This is due to the fact that background, for instance, is way easier to segment than vessel wall or lumen. Then it makes sense that the distribution is clustered to 1 for the background. So now, to give even more insight on how different are all those experiments, we took, for a given patient, this is the same patient, 3 models that segmented the carotid artery. The first one performed poorly. The second one performed better, but as you can see, we still have 2 lumens instead of 1. And finally, the third one performed correctly. We also shows here the 4 uncertainty maps to explain that every uncertainty map has its own strategy to assess uncertainty, and this can be seen on how different the different uncertainty maps look like. Now let's answer the question of the beginning of the talk: which uncertainty map should I use? And to do so, I will discuss these figures, which is the distribution over the test set of the area under the precision recall curve for the different uncertainty maps. So what we can see from there is that the averaged variance and entropy performs better than the Bhattacharya coefficient and the Kullback-Leibler divergence. Also, the averaged variance performs similarly as the averaged entropy. Finally, we can see that the Bhattacharya coefficient is better than the Kullback-Leibler divergence. To assess how significant are our results, we use the posterior distribution of PAB, the proportion of experiments where uncertainty map A is better than uncertainty map B. The rules to read this diagram, this figure, is the following. If PAB is equal to 0.5, there is no effect. If PAB is above 0.5, uncertainty metric A is better than uncertainty metric B. If it's under 0.5, it means that uncertainty metric B is better than uncertainty metric A. Then it confirmed the precedent results we showed in the precedent slide, as average variance and average entropy have a distribution of PAB centered on 0.5, and for all the others we have a clear answer. And this clear answer shows that for every association of metric except averaged variance and average entropy together, we have a clear answer on which uncertainty map is the best. And this answer is significant. So in conclusion, I would like to remind that description strategy is better than similarity strategy, that Bhattacharya coefficient outperformed Kullback-Leibler divergence. We would recommend the use of averaged variance, as it requires less approximation, as we showed in the paper. And our results are consistent with the literature, as the description strategy is much more used than the similarity strategy. I would like to thank an UNSURE workshop for giving me the opportunity to present my work. I would also like to thank my co-authors for the great work we did together. And finally, I would like to thank you for your attention. You can reach me by mail. Goodbye.